lecture we will consider the second important theorem regarding CW complexes after the first one that has been covered in the lecture 1.4. Lecture 1.4 we showed that by collapsing a contractible sub-CW complex we get a homotopy equivalence. Now we prove the second fundamental theorem regarding CW complexes. Notation: let A in X be two topological spaces and F a map from A to Y. Y is again another topological space. Then we will denote X disjoint union with Y over F. F is the map, to be the following quotient topological space. We take the disjoint union of X and Y and we mod out by the equivalence relation described as follows. We take an element of X and we declare it to be equivalent to an element of Y according to this equivalence relation if and only if X belongs to the subset A, the subtopological space A, and Y is its image in capital Y. We can now state theorem 2. Let X, A be a CW pair and Y be a topological space. Suppose to have two maps F and G from A to Y, and let's assume that these two maps are homotopic. Then X union Y over F has the same homotopy type as X union Y over G. So this is the statement. Proof: the strategy is to find an intermediate topological space Z with homotopy equivalences I and J. So we want to show that this space is has the same homotopy type as this space. Well, we will see that it suffices to find two homotopy equivalences, one from the first space to some intermediate space Z, and the other homotopy equivalence from the second space to the intermediate space Z by another map J. We plan to use the HEP that we introduced in the previous lecture, which stands for homotopy extension property, on the CW pair X, A by means of the following proposition. A CW pair XA satisfies the HEP if and only if there is a deformation retraction R from X times I is the unit interval, to this space X times 0 union A times I. If you have learned lecture 1.4 before listening to this video, you will be accustomed to the map R, and especially to this space right here, which comprises the base of this cylinder and the cylinder over A. A is a sub-topological sub-CW complex of X. Notice that there is nothing special about 0 here. We could have taken 1 as well and get the same result. So we will be using the fact that the retraction can go from this cylinder to X times 0 union A times I, or X times 1 union A times I. We will use this fact in a moment. In that lecture, we did not use that R was an homotopy equivalence, remember? We just used that it was a retraction. However, we will need now that R is a homotopic equivalence, so we are going to use it for the proof of theorem 2. Let H be a homotopy between F and G. I remind you that F and G are two maps from A to Y, and we set Z to be the following space. We take the union of X times I and Y along the map H, the homotopy H. I remind you that H is a map that goes from A times I to Y. Let's draw a picture. In the particular case, X is D squared, the two-dimensional disk, and A is its boundary. So we first draw the topological space obtained as the disjoint union of the two-dimensional disk, which we set it to be X, and a topological space Y through a map F. X is a two-dimensional disk. The boundary is the S1, a circle that embeds in the boundary of X. The map F is defined just on the boundary, which we define to be A, and it will have some image here in Y. The image can be much worse looking than this, but just for displaying purposes, let's assume that the image is this. If we take X disjoint union with Y along F, what do we get? We get the quotient space by X disjoint union Y mod out by the equivalence relation induced by F, which glues together points of the boundary, points of A, with its image here on Y. We take a point here, we look at its image, and then we glue together the disjoint union of X and Y along this equivalence relation. So points that of X and Y that are not in the image of F of A or are not in the boundary of X, they just go there untouched. And something happens just on the boundary of X and on the image of this A inside Y. Therefore, what we get is something like this. We get the disk X glued on Y along the image of its boundary inside Y. Y with the cell attached to it. Okay, so keeping this in mind, let's see what we get if we draw this more complicated picture regarding Z. Inside Z, we will find two subspaces. One it will be X union Y along F, and the other is X union Y along G. We are assuming that F has this image, so we are attaching a two-dimensional disk along the image of F, and the image of G is somewhere else in the space Y, and we will attach the disk D2 along the image of G. So if you see here, we are attaching a family of disks parameterized by I. Okay, so X is D2. D2 times I is a family of disks. And for each T in I, we have a disk D2 with its attaching map that is given by the restriction of the homotopy to the same T. Therefore, we get Y with a family of disks attached that go from the disk attached through F, which is one extreme, and the disk attached through G, which is on the other extreme, because the homotopy H is a homotopy between F and G. Remember that. So for H restricted to A times 0, for example, we are here in the orange cell, and for H restricted to A times 1, we are here in the cyan cell. And for a generic T between 0 and 1, we will be getting some cell attached to I some cell in between these two initial and final cells. So this intermediate one will be a cell attached to Y via the homotopy H restricted to A times a value of t between 0 and 1, some intermediate value, where this is the homotopy between F and G. So clearly we have an inclusion of this space inside Z, and of this space inside Z again. Now we have two deformation retractions, RF and RG, the first one going from x times I to x times 0 union A times I, and x times 1 union A times I. Remember that I said that if XA satisfies the homotopy extension property, then there is this deformation retraction onto of x times I on the cylinder on x onto x times 0 union A times I, but we also have 1 on x times 1 union A times I. Now, why do we have that? Because, as I said, XA satisfies the homotopy extension property. But why is that? Because we proved in lecture 1.4 that if XA is a CW pair, it does satisfy the homotopy extension property. Okay? So by the proposition above, we have both RF and RG. RF and RG induce deformation retractions, capital RF and capital RG. The first one going from Z, so this space here, to the one up above, X disjoint union Y over F. How do we get this deformation retraction? We get it by using this RF retraction right here. Okay, so essentially this capital RF retraction, it takes all this part, all these cells attached from here to here, and squeezes them down on A times I, and the image of A times I is the images of all the attaching maps right down here on Y, right here on the bottom, and the missing part of the cylinder of X that gets squeezed on the base. So this base here gives this cell, and this A times I, all the images of the attaching maps. So everything else that is missing gets squeezed down on this remaining space, which is just this. This retraction RF induces capital RF, and it is a deformation retraction as well. Just in the same way, we have capital RG that takes, uses this retraction here on X times 1. Why we look at X times 1 now? Because X times 1 gives, once we attach it on Z, gives this cell. So this cell survives. A times I, once again, is all the union of the images of the attaching maps here in Y. Everything else gets squeezed down, and what remains is just X disjoint union with Y over G. So what we have proven so far is that the space right here on the top is homotopy equivalent to the space Z here in between via these two maps. These are inverses, these are homotopy inverses, one each other. One is I, that is the inclusion, and the other is capital RF, that is the deformation retraction on this space. So these have the same homotopy type of Z, and then this other space has the same homotopy type of Z exactly by the same argument. what we want to prove, remember, is that this space has the homotopy type of this one. So we have to somehow compose two homotopy equivalences in order to find one big homotopy equivalence from this space to this. And while we have not proven that yet, but homotopy equivalence is an equivalence relation. In particular, it is for that it holds the transitive property. Therefore, if this space is homotopy equivalent to this, and this is a homotopy equivalent to that, then the first one and the third one are homotopy equivalent. Let's prove this explicitly. Once we have that, we have finished the proof of the theorem. We conclude the proof of the theorem by using the following lemma: homotopy equivalence is an equivalence relation. In particular, it is transitive. We will be just using this property for finishing the proof of theorem 2, the transitivity. The other two things to prove in order to make it an equivalence relation are the symmetry, one, and the reflexivity, the other. So they are pretty straightforward. Let's focus on transitivity. In general, we have two homotopy equivalences from C to D, and in one direction is alpha and the other direction is alpha prime, and then we have other two homotopy equivalences from D to E. One direction is beta and the other is beta prime. Now let's give a name to the two homotopies that make these homotopy equivalences. That is H. H is a homotopy between the composition alpha prime composed with alpha and the identity of C. This is the definition of homotopy equivalence between C and D. The other homotopy, we call it K, and it will be from beta prime composed with beta, so first beta and then beta prime, and the identity on D. We will just prove for this because the homotopy equivalence implies also that if we compose these morphisms the other way around, so for example first alpha prime and then alpha, that will have to be homotopic to D. The proof is just going to be exactly similar to the ones we are making right here. We want to construct a homotopy N between. Now, what we want to prove is that C is homotopy equivalent to E. So we need to go from C to E and backwards and show that the composition going from C to E and backwards is homotopy to the identity of C. Okay? So our candidate, given this data, for going from C to E is obviously just going from C to D with alpha and then with beta and then coming back applying beta prime and then alpha prime. So we are looking at a homotopy N between alpha prime composed with beta prime composed with beta composed with alpha and the identity of C. Now let's draw a picture that will construct the homotopy we are looking for. So here we have C times I. Our homotopy will be a map going from all these cylinders to C. And it will have to link the following functions that we listed right here. One is this composition, this like a 4-tuple composition, alpha, beta, beta prime, alpha prime, and then the identity of C. Somehow we have to use the homotopies H and K in order to fill up with the map going from all the cylinder instead of just going from the base on the bottom and the top of the cylinder. So let's take the restriction of a cylinder to C times U. U is going to be the parameter of the homotopy. And let's take first U comprised between 0 and 1/2. So this is C times U, so basically is homomorphic to C. We apply alpha to it and we end up to D. Then we don't apply beta and beta prime, but we directly apply the homotopy K at the level 2U. 2 times u. So in this case, it's like we are squeezing the homotopy of the homotopy K. It is the homotopy of beta beta prime with the identity on D, and we have to squeeze it in order to make it fit between its parameter from 0 to 1 over 2 to 1/2 instead of from 0 to 1. This is why we multiply by 2u here. Okay, so we just bypass E and use instead the restriction of the homotopy at this level here. When we end up at 1 over 2, what we have? We have again alpha, so we go from C to D by alpha. And this homotopy, meanwhile, assume the value of D times 1. And at D times 1, this homotopy is the identity on D. So here we go from D to D just by the identity. And then we apply alpha prime, just like before. Now, how do we feel the homotopy in the upper half of the cylinder? So we take again a u between 1/2 and 1 at this point. We skip directly D, and we apply now, instead of alpha alpha prime, we apply the homotopy H between alpha alpha prime and the identity of C, reparametrized in order to make it fit from 1/2 and 1. And finally, when we will be for u at level 1, this homotopy will be also at level 1, and by definition, at the level 1, this homotopy is the identity on C. Okay, so this is the definition of the homotopy that we have between this composition and that goes from C to E and backwards. So this one goes from C to E, and this one comes back, and the identity of C. So we have that C and E are homotopy equivalent. This finishes the proof of the lemma and the proof of the theorem.